Welcome to Essential Problems with CRIP. Given this prompt, an important process for the production of acetonitrile, C3H3N, a key component of main polymers, is given by the following reaction below. A 150-liter reactor is charged to the following partial pressures at 450 degrees Celsius. Assuming the reaction goes to completion, what is the total pressure of the reactants and products if it is collected in a separate vessel of 500 liters at 100 degrees Celsius, in which 1 atm is equivalent to 101,325 pascals? The first thing we should note is for the initial conditions that our initial volume is 150 liters and the initial temperature, 450 degrees Celsius, is 723 Kelvin. We should then immediately realize that we need to convert the pressure of C3H6 in megapascals, mega being 10 to the 6th, to atm, and the pressure of NH3 to convert that to atm, and then the pressure of O2 to convert that as well to atm. The next thing we need is to find the individual moles of C3H6, NH3, and O2. Of course, since we have the volume and temperature, we can now use the ideal gas law to find moles of C3H6 and the moles of NH3 and the moles of O2. Once we're at this point, we have a limiting reagent problem. Notice that we have the exact same number of moles of C3H6 required as the moles of NH3. Given this, we can already see that C3H6 is limiting in reference to NH3. So all we have to do is convert the moles of O2 to C3H6 needed to react fully with this in order to determine which one's limiting. And with a simple conversion to convert to moles of C3H6 needed, and that's important that that's what's needed to react fully with this, that we realize that the actual amount of C3H6, 12 versus 24, that this, the actual amount, is the limiting. So here above the C3H6, we can indicate that is the limiting reagent in this problem. So now we're ready to create a BCA table. That is a before, change, after table in reference to our balanced chemical equation. And you will see how important this is in reference to the problem. So we should, let's see if I can just block this out for now, because that will be for later. So now what we can do is indicate the quantities at before. So here we have the C3H6 and the quantities of NH3 and the quantities of O2. And so I can put them right there. And these again are in moles, right? The moles of C3H6, the moles of NH3, and the moles of O2. Now, when we determine the limiting reagent, what that does is it allows us to put for after that this value for C3H6 will be 0. Now, based upon the balanced chemical equation, the coefficients in the balanced chemical equation, we can indicate the change that will occur. So the change that will occur for C3H6 is minus 2x. The change that will occur for NH3 is minus 2x. And this minus 3x for this in producing plus 2x, and for this in producing plus 4x. Since the before plus change is equal to after, so before plus negative 2x is equal to 0, we can solve for x, and x is equal to this value right here. By doing this, now we can substitute in for x and solve for all the other moles. So these would be the moles of a reagent left over. Since they're not limiting, they would be excess reagents, and this would be the moles of acetonitrile generated and the moles of H2O generated. Finally, we can easily calculate the total number of moles by adding these together. These are the total number of moles of gas generated, and we have a new volume, V final, 500 liters, and we have a new temperature, 373 Kelvin. To find the total pressure, we need to do one last equation in which we find P total by using the ideal gas law equation and substituting in. We can solve for the final ATM and rounding to the correct number of sig figs. This is 3.90 ATM. Till next time,